Yeah, so hi, I'm Alex. So I'm a postdoc at Northwestern in the Department of Material Science, but my PhD is in physics. So you'll see that what I do I would say is quite interdisciplinary, and it kind of has to be when you're working with materials. And yeah, so I'm a computationalist or theorist, depending on how you want to think about it. But basically, what I'll talk about here are a few questions and some answers, which I think we've provided in correlated electron systems. Um, okay, so you've maybe heard this term quantum materials quite a bit recently, and most of these materials fall into one of two categories. So one is topological materials and one is correlated electron systems, and I'll focus on these ones. And I have a YouTube channel as well, so I should advertise it, where I talk mostly on correlated electron systems, and you can also see some other talks at different levels. So yeah, so I have some work on topological materials as well, but that's not what I'll focus on. I'll focus on correlated electron systems, though I should mention sometimes band topology makes some materials be correlated, but that's a separate story. But the reason these materials are usually interesting is for things like metal-insulator transitions. So you have a material that has a sudden shift in conductivity. Magnetism, so fridge magnet is a quantum material. For electricity, so materials that have an intrinsic electric field, for example. And maybe the most well-known one are things like high ATC superconductivity. And an interesting thing I found out about recently, if you want to watch a bunch of cool talks on high TC superconductivity from around the time it was discovered, there's the Woodstock of physics on YouTube, and it's really interesting to see how people thought about things at the time. And these things are all very useful for things like novel and low power electronic devices, as well as things like quantum computing. And again, magnetism is a quantum property in materials, and it's just, and I'll get back to why. High TC superconductivity, you've probably heard of like BISCO, for example, and here metal insulator transitions. So you have this sharp change from an insulating state to a metallic state. In combinations of these, layers of layered materials are very interesting, right? So we don't really use these hard drives in our computers anymore, but in supercomputers, they're still there. So this is a hard drive with a hard drive reader. And the Nobel Prize was actually given for giant magnetoresistance, which is a resistivity shift as a result of a magnetic field, right? So you have this reader and you have changes in magnetic field. Have a change, you have 1. If you don't have a change, you have 0. It's not actually the orientation. And this was a Nobel Prize for the technology it allowed us to use. Possible applications of correlated materials can also be apparently less high tech, right? So you can have things like smart windows that just turn darker when there's a lot of light outside to protect you from UV and protect you from needing to use a lot of power to run your AC, for example. And another cool different type of device people are thinking about building are neuron mimicking computer architectures, particularly say using metal insulator transition compounds. You apply a field and the whole thing becomes metallic. And in terms of spin liquids, there's in quantum computing, spin liquids should in principle be very important. There's no spin liquid material confirmed yet, but the idea would be you'd turn a spin here and the one over there would turn with it. Okay. And there's also other possible applications, for example, dark matter detection. Right. So in these materials, they have all these different types of competing phases. So just like with something like water, where whether you have a solid or a liquid or a gas, the phase the material is in matters a lot. And often the material at the surface might kind of look the same in different phases, but in one phase it might be magnetic, in another phase it might be conducting. So you can think of like water flowing, in the other case insulating. The electrons are locked in place, right? So things controlling the phase of a material basically means allows you to control the useful property, and that's what allows you to actually use that material. And one of the things that's maybe a little bit less studied in the field, though it's definitely studied in other branches of material science, is that phase transitions are often heterogeneous. So here I'm showing, pancake ice on Lake Michigan, which we'll see here again soon in a few months. But as you can see, the lake doesn't just freeze all at once. It doesn't all actually freeze. You'll have different patches of different phases. And similarly, in these compounds, you won't actually have a uniform transition. Okay, so what is kind of driving these correlated electron materials, particularly the ones I'm interested in? Well, the ones I usually look at have a transition metal in them. They're solids with a transition metal in the composition. And they'll often have some sort of specific ordered electronic configuration in the d orbitals of the transition metal side. So here I'm showing a magnetic moment, but you can have other types of order as well. And you have these atoms, they communicate with each other through other parts of the material, and this will lead to long-range order. So if these spins on the different atoms align, you will have, for example, ferromagnetism, right? If the spins would be randomly oriented, you wouldn't have as much of a useful state, right? So again, here I'm showing ferromagnetism. So one way to think about this is just as emergent phenomena arising from localized states in a bulk material. And the atoms can be connected in a variety of ways. So you can have materials where the atoms are connected in triangles. They have different anions. So anions, I mean here, for example, perovskite oxides, you have this electronically active transition metal site, but it's talking to the other ones through oxygens. So they'll have a local ionic environment around that determines the properties as well. Okay, so one of the things that we've been getting quite good at is understanding the interaction between the electronic structure and the crystal structure. So one example is high TC superconductivity in cuprates and nickelates. And I should actually mention, when people were initially searching for superconductivity in cuprates, we were also thinking maybe it might happen in the nickelates as well. And again, I would refer you to the physics Woodstock lectures that happened at APS. So suppose you take this atom in a vacuum, here, copper. And if it's in the vacuum, you'll have d orbitals or degenerate, you have spherical symmetry. Okay, this is the stuff we learn in quantum. And you put this atom in a cubic environment. The cubic environment breaks the symmetry, and you'll have two different types of orbitals. You'll have these EGs and these T2Gs. The T2Gs point away from the oxygens, the EGs point at them. And if you have a further symmetry breaking, you'll have a d orbital splitting. So for example, here I'm showing these two orbitals, and the reason they end up having different energies as well, this one is pointing here, so it sees less of the oxygens, is less repelled, so it's going to be lower in energy than this orbital here, which still sees these oxygens at the same strength, right? And people often refer to this as a Jahn-Teller distortion. Many things are Jahn-Teller distortions, and this is the most well-known, and I'll get back to my many things are Jahn-Teller distortions. Okay, so suppose you have 9 electrons in the copper D shell. Well, you then have this electronically active orbital, right? So these are all filled, and this is what gives you the physics. And people build all sorts of complicated models to understand cuprate high temperature physics based on this one orbital model that hops through the oxygens. One of the interesting things is that this distance between the copper and oxygen along this direction is associated with particular energies, charge transfer energy I won't go into, but it's basically a energy difference between the D states on the copper and P states on the oxygen. And this is associated with the strength of the magnetic interaction, and this seems to then lead to a change in TC. So, the structures aren't fully equivalent, so this isn't like a flat line, right? But this change in copper-oxygen distance does seem to tune the TC. So again, structure drives electronic properties. But so then this led to the question, can we design nickel-based superconductors based on the same premise? So what does that mean? Well, we want to have the d orbital split, and we want to have all 9 electrons. So we have this similar model. And this is something I've worked on quite a bit during my PhD, building, I wasn't building, simulating heterostructures people would build. But that didn't lead to a superconductor. It was proposed, this methodology was proposed over 20 years ago. And yeah, it's actually turned out to be possible. So, neodymium nickel, which is now very famous, and Harold Fang's group, the way they did it wasn't through complicated heterostructures, still a complicated synthesis process, where they just took away these apical oxygens, right? And this is how you have a similar electronic structure, similar up to a point, and you have high TC. Well, unconventional superconductivity. Okay, so predictive theory of the electron lattice interaction can lead to new materials. And it used to be that experimentalists actually had a rule to avoid what theorists propose as a new superconductor. It looks like with these nickelates, that's not the case anymore. So increasingly, we're getting confident that we can build some rules and can predict new material properties before they're synthesized. Okay. Another interesting thing is that, as I was showing you, you change electronic properties, but the atoms themselves actually move very often. And this can be a problem in some cases. So for example, VO2 has a metal-insulator transition. And as it undergoes this transition, the atoms can move, and this can lead to the material actually breaking. So, or material fatigue over time. So this is something we generally kind of want to avoid, and it's it's one of the reasons that kind of motivates the question is, can we have some materials where the transitions are electronic only? Okay. And the other reason is that ions move slower than electrons. So if you want to build, if you want useful materials that don't break and that switch fast, you really want to look at the previous pictures I was showing and try and tune things in such a way that phase transitions move the electrons much more than, and don't imply the lattice that much. Okay, so I'll talk about 3 different topics. The first one is actually this local theory and control, and basically how to separate the electron and lattice degrees of freedom through a phase transition. And this was published this year in Communications Physics. We go into a lot of detail, and I show a little bit of that. Heterogeneity of phase transitions and how we've addressed that using heterostructures. So basically like sandwiches of 2 different materials. And yeah, this is a Nature Materials a while ago, as well as materials discovery. So in this paper, we basically built a machine learning tool and a database for materials that have a particular property, so metal-insulator transitions in this case. Okay, so again, let's focus on this topic first. And this actually started off with a previous paper, so also working with Andy Melis and Antoine Georges, when I was a postdoc at the Simons Foundation at the Center for Computational Quantum Physics. And this was published in PNAS. So, have a metal insulator transition. How is it useful? Well, the way things usually work is you have one of these MIT materials at low temperature, it's insulating. You heat it up, it reaches this TMIT, it becomes metallic, so you have a sharp drop in resistivity, and you can keep raising the temperature. Okay. And these plots don't always look exactly as sharp. So, for example, these are different heterostructures with neodymium nickelate, which is an MIT material. And the bulk material here, you can see, basically has this structure. These other ones, it's a little bit harder to see, or they're at higher temperature. But basically, when you design an MIT material, you would rather have it have this sharp transition for it to actually be useful, right? How do you separate 0 from 1 in a device? You have to have a strong threshold. And one of the things about these materials is that, as far as we know, there's around 60 of them that are thermally driven, and they have a wide variety of possible mechanisms that lead to this metal-insulator transition. And the reason these are useful is, well, in your computer, you wouldn't want to heat it up and cool it down. The thing you do is you actually take the material, have it where it's insulating, and then you apply an electric field, and then you can force it to become metallic. And then here there's another question: is it heating up? Is it doping? But the point is, you can force it to become metallic, and that's why it's actually useful in electronic devices. Okay. So that will look something like this. You have some voltage and you have a current. You reach a particular voltage, the material becomes metallic. And this is what people used to do, things like build neuron mimicking devices. And, this is an interesting example. I think this is niobium oxide. Okay. And these are also materials you can use for the smart windows I was showing. So, metals are shiny, right? That's why we use them, for example, in mirrors, and insulators less so, often transparent. So you can think of, any photon that comes to this electron C in the metal is just reflected, right, by the sea of electrons. So the point is that if you put this material on a window, it's insulating, you have light come in, heats it up, or just excites the material in some way, it makes it shiny, starts blocking out more light. Other things are, infrared detectors, again, just have light come and make it metallic, and you can feel that in a sensor. Okay, so useful MIT materials then have to have a temperature of transition above room temperature, right? You have to be able to operate with them when they're insulating. You'd rather have a sharp transition like I was showing, and a minimal ionic lattice change throughout the transition. So if you could actually avoid this altogether, that would be best. To make them faster, more efficient, less likely to break, right? Okay, so the question then is, how can we figure out if a particular material can have an insulating state without moving the ions? Or like a switchable state where you don't move the ions, you just change the electronic state. Okay, so this is a very old problem. If you read articles from the 80s, for example, on the Jan Teller effect in a variety of materials, this is a question that keeps coming up. And usually the problem is we have electronic structure codes, right? You have an atomic structure, they give you an electronic configuration. It's a little bit harder to change the electronic configuration and see what would happen to the lattice. And this is basically a problem we solve. And how do we vary both? And this is a solved problem. And the basic idea is, if you take, for example, the rare earth nickelates, right? So their high temperature state, they look something like this. The rare earth is here kind of inert, it just gives some electrons. And you have these nickel oxygen octahedra in the middle. High temperature state, these all basically look the same. Okay, and you can think of this as having, 1 electron per nickel. The I'll get back to this. This isn't necessarily true, but on average is 1 electron per nickel. Okay. And as you lower the temperature, you have a breathing distortion. So, this is what the breathing distortion looks like. One thing becomes bigger, one becomes smaller. And then you have more electrons in a particular picture, you have more electrons on the nickel here than on this nickel. So you can think of them as 2 and 0, though they're more likely to be, 1.6 and 0.4, but something like this. And then the thing is, how do we define the order parameters? Like when I say the lattice shouldn't move, can I just pick one number to define that? And the answer is yes. Well, we have this breathing distortion. Bonds become longer or shorter. So then this bond disproportionation can just be the difference in bond lengths between the nickel and oxygen. So between this octahedron and this octahedron. And then the electronic part can just be the difference in electron occupancies from this one to this one. Okay, so now I have electronic and a lattice parameter. And then we can define an energy relative to the metallic phase, right? The metallic phase is the one where there's no distortion, there's no breathing distortion, there's no electronic part, no electronic distortion like this. So there's a spring stiffness. So there's a stiffness of the nickel-oxygen bonds here. They don't want to be disproportionated. There is a coupling of the electron and lattice part, which is linear. I should mention it doesn't have to be linear, but we found that it's linear. It's kind of like an electrostatic part, right? So you move an oxygen, you change the electric field, the relative electric field on these two. It's kind of like a chemical potential difference times electron number, right? And then you have an electronic part. And this electronic part, I calculate with dynamical mean field theory. So it's a method that's a little bit beyond like the standard band structure, electronic structure methods we use. You can think of it as including the multiplet states on the transition metal side. So you can think of a superposition of 0 electrons and 2 electrons. And some of the electrons in one state might have one spin configuration, the other might have another spin configuration. So this is something that can be done. And this is basically the electronic part only. Okay. And the novel aspect of this work is actually how do we calculate this thing? Like how do we separate these things? And, it's a little bit tricky, but the basic point is that once you write this down and you're able to find these coefficients from calculations, if you take a derivative of this energy with respect to Q, so, the breathing distortion, right? You just move the atoms, you take this derivative. Well, the derivative with respect to Q, if you set it to 0, that gives you Q as a function of delta n. So in this case, this stationarity actually tells you what is the optimal Q given a particular delta n, right? So the electrons have moved this much. Where would the lattice be? How much would the atoms have moved? Okay. And then this is kind of a linear lattice response, right? The electrons move this much, the atoms will move to respond to some electrostatic fields. Probably going to be linear if the electrons don't move that much. Okay. And then from calculations, we move the lattice and we get a difference in electrons. So this is this delta n as a function of Q. I should mention this is the most technical part of this talk. It won't have as many equations. But the basic point then is that you can write a polynomial of this form and using these stationarity equations, actually figure out what the terms A, B, and C are. Basically, you apply a field, an energy difference between the two, and you see how the electrons respond and how they disproportionate. And this actually allows you to get A, B, and C. And then you build an actual energy landscape as a function of the ionic degrees of freedom. So how is the material distorted and how much do the electrons move? So you get something like this. So this is the plot for neodymium nickelate. And this is the metallic phase where everything is 0. And then you have these two insulating phases that are distorted. And they're symmetric because it doesn't matter which way the breathing distortion is, like which, right? It's like a checkerboard. It doesn't matter how you pick the colors. Okay. So I was showing you that you find A, B, and C. Well, this allows you to get this electronic energy here. One of the interesting things is that you find that for lutetium nickelate, you might get the state here that's insulating, even at the electronic only level without adding the lattice, but it's metastable, so that's a separate story. And then this term is basically always positive, right? The electrons always oppose the disproportionation. They'd always rather be here. This part is the lattice part, the spin constant. It also always would rather be positive. So this is the only negative term. So this is then, this electron lattice coupling is really what stabilizes this insulating state, right? So this is then the total energy, and you can see that these are insulating, and this one isn't, and this is probably due to a choice in parameters, and the calculations are paramagnetic. But the basic point is that this is really what drives the transition. So the electrons and the lattice are moving together rather than each one individually. And this is a pretty key point, as again, this is a very long debate. Okay, so this is an energy landscape for neodymium nickelate. And again, we've clarified we need the lattice part to be distorted. And of course, we need the electronic part to be distorted to be in this insulating disproportionated state. So maybe, yeah. Okay. One of the interesting things is this is very computationally efficient because of the particular way I do the fitting. Okay. The energy landscapes can also be very different from one material to the other. So people have also built energy landscapes kind of phenomenologically from experiment. And here, basically, they found that if you force a particular material in a particular way, I'll get back to how you do that, but you can actually have an electronic switching without the lattice switching because it's just forced by another nearby material not to allow the atoms to move. And again, this would be very useful for actual fast switching, electrons only moving, not the ions doing this. Okay. So in these rare earth nickelates, one of the things I was showing is that the materials with the more bent bond angles have a higher MIT. And we can now kind of explain why. So why the transition is at the higher temperature. And it's a combination of electronics and also softer bonds. The material, the lattice itself is has a lower cost to becoming disproportionated. But so as I was mentioning, you have less electron hopping, right? So in here you have more rotations. It's harder for the electrons to move. It's more insulating, and the lattice stiffness K goes down. So again, more rotations, more insulating. And the thing I should mention is, I'm not going to go into all of these exhaustively, but the basic point is that in this one paper, we've actually covered bulk nickelates. We've covered some heterostructures. We've covered another type of material, calcium ruthenate, as well as calcium ruthenate grown on a substrate. And one of the nice thing about this methodology is that, as you could see, a big part of it is actually, after you do the calculation, you get a lot of like modeling power. So you could actually simulate what happens as a result of changing this substrate and its lattice constant and how it pulls on the oxygens. Without actually doing a new calculation, we could just do a change of variables. So yeah, I shouldn't go into more detail on that, but basically this paper is quite exhaustive on that. Okay. And it's also widely applicable. So this paper is actually in PRB. We can apply it, for example, to two-dimensional halides and trihalides to understand the role of lattice symmetry breaking in the different modes there. And there are some interesting open questions. So one of them is that all these methods, they say the method I was showing treats these local electronic states on a transition metal. That's not necessarily the full picture. So you often have fluctuations between the transition metals of the electrons, for example, in superconductors, right? And then you also have lattice vibrations. So we don't include those in this method. And that's one of the reasons why, our transition temperatures are much higher. So for neodymium nickelate, which has a transition temperature of like 200, we get over 1000. So there's a big question there of what the actual, what actually makes the material go metallic. So, okay, figured out what stabilizes the insulating state, but as you change the temperature, what actually kicks it out of that? That's a little bit trickier. And again, this might be like role of lattice vibrations, phonon entropy, and so on. All right. Another thing I feel is missing, and this is one of the things I guess I kind of mentioned as like an open question or something I feel like is often missing when we do these computational techniques. And I found it kind of interesting to see how people thought about them before, you could just do computations. For example, in this really great book, was people would work through the Jahn-Teller theorem in excruciating detail on the different symmetry modes and so on. So if you're not familiar with the Jahn-Teller theorem, what it generally means is that and this is in very, very broad brushes, but the basic point is that usually if you have some sort of degenerate state, often whether it's a molecule or a solid, so, two states with the same energy, you will have some sort of spontaneous symmetry breaking. It doesn't always happen, but the general point is that, your material will not want to be in the superposition of two states that are the same, or your molecule and so on. So this depends a lot on your symmetry, but to give you like a very boring example of how this would work is just if you have a 2x2 matrix, and it just has these two eigenvalues, right? This is your Hamiltonian, and there's nothing in between here. There's no off-diagonal part, right? And say there's some sort of symmetry protection against there being anything here. Then you have two degenerate eigenstates, fine. So sorry, there shouldn't have been that arrow and minus d there. Okay, but suppose your symmetry is somehow broken, and you have some perturbation here on this off-diagonal part that connects these two eigenstates. Well, by default, you'll have one eigenvalue at least be lower, right? You'll have one higher, one lower. But the kind of way to think about that is you will lower the energy of the system by breaking symmetry. Now, this is really oversimplified. I don't think this 2x2 matrix really corresponds to any particular material. But this is kind of the general idea. You will usually have some sort of large matrix. You will have some perturbation terms. And in almost all cases, first order perturbation theory symmetry will be lowered, with one exception where it's second order, but it still will be lowered. So the question to me is, I was showing all this computation, but is there a clear way to write down, say, Jahn-Teller theory for the nickelates? And this is kind of the thing I think is kind of missing, right? So, this is from Wikipedia, so you can read a lot about the Jahn-Teller effect, of course. But basically this picture here where, you break symmetry and you lower the electronic state, right? Looks pretty familiar. You can also have other forms of symmetry breaking but I won't go into that. This is more relevant, say, for electrics. So here where you have this type of symmetry breaking, one question then is, is this metallic state really one electron and one electron? So say, or is it some sort of superposition of more electrons and fewer plus the reverse, and then you're kind of breaking the symmetry. So this is something you're interested in looking into. Please just let me know. because this is something I've been thinking about for a while. And it's kind of just something we don't really think about as much many times, right? In my case, just do a calculation. This is metallic undisproportionated. But the actual state might be a little bit more complicated than what it looks like. Okay. So heterogeneity in phase transitions. So I was showing these are heterogeneous, and to give you an example, this is neodymium nickelate actually undergoing a phase transition. And it has different patches of metal and insulator. So I should drink some water. So that's why it has that hysteresis loop you saw, where it didn't all transition at once. So that basically, the way to kind of think about it is that you'll have different transition temperatures for different regions. You'll have metallic, you'll have insulating stripes. So one question is kind of what leads to the size of these stripes. And again, you can see here, one of the issues is because this is non-equilibrium, it's a little bit harder to kind of simulate it. Most methods we have are aimed at like the ground state, so the optimal state the material is in. And we kind of need theory at longer length scales than accessible by DFT. So the tools we have, I was showing you like 20 atoms or something like this. This is of the order of hundreds, thousands of atoms, probably actually more. So it's not trivial to simulate these things, especially with all the extra electronic parts. So one way to approach this is to just take two different materials that have two different transition temperatures, right? Kind of like the different stripes, and see what happens. And these will have very different transition temperatures, but the same mechanism. So, sorry, this is all in this paper about how this was done. And basically, experiment was done at the University of Geneva, EPFL, ETH Zurich, and Vienna, and Jean-Marc's group. And, I should mention this is a really, really great collaboration talking to, just really great students and postdocs, and basically, and of course, professors. And basically, one of the cool things is, this started before lockdown, so it actually started at the poster session in the mountains in Diabler, Switzerland. So, it's pretty great. Okay, so the basic point here is you have two nickelate materials. They have two different transition temperatures, right? Samarium nickelate here, neodymium nickelate here, put them together. And the transition temperature will be shifted a little bit because they're grown as thin films on another material, but they end up looking like, 100 Kelvin, 350, 400, something like this. And when you actually build a superlattice, you will have either one transition or two. And the interesting thing is you can see here there's 7 unit cells of each, and you still have a single transition. And then you start having two. And this looks something like this. They had this phase diagram, and then the question is how do we explain this? And again, here, one transition, both materials at the same time. Then you have here, all the material is insulating. Here's some of it, like half of it transition to a metal, and then here the whole thing becomes metallic. And this is a pretty remarkable 18 cell length scale. And we also found that there's very limited intermixing, right? So if you've never seen these types of EELS compositional maps, it's basically electron microscopy, like shoot electrons at the material, see at what energies the electrons are absorbed. And it's really interesting because, you do this at with atomic precision, and then you can really see, well, this is neodymium, this is samarium, this is neodymium. And, this isn't, so this is really this very complicated, just heterostructure. And the basic point was that to the theory I was showing before, you can add temperature part. So just how does the how does the relative energy of the metallic and insulating state change relative to each other with temperature. And you also have this constant electronic and lattice mismatch, which we assume is constant because it's a first order theory. So shouldn't really go into this, but it's very similar to say nucleation and freezing water. When you have a first order theory, you really just have a cost that's very short range compared to everything else. So this cost is limited to this interface. You have this constant phase boundary. So this actually comes from a gradient term, which we then realize isn't actually more than we need. So what ends up happening is that you have a competition between this phase boundary cost, so between SNO and NNO, and the cost for each material not being in its favored state, right? So NNO in this case would really want to be so half the material would want to be a metal here all the time. But here, the cost of having metal plus an insulating state would be too high, right? So you'd force this material here into being metallic. So, sorry, let me rephrase this. This phase boundary cost is quite high, right? So it is enough to lead to a single transition rather than have this state where some of the material is metallic, some of it is insulating the way they would want to. They're just forced to all have one transition to avoid this thing. Okay. And, I should mention, I'm not going to go into details, but basically we built a theory that has just 3 parameters and it matches perfectly with experiment. Okay. One of the interesting things we get from this theory is that this length scale of the transition is inversely proportional with a difference in transition temperatures of the 2 materials. So if you have an MIT, that's a single material with different regions rather than 2 materials with like this 200 Kelvin difference. You have one material with 10 Kelvin difference. It actually corresponds pretty well to what you see here of hundreds of unit cells instead. Okay. And one of the interesting things is a main assumption that people might have wondered about is why do we say there's a phase mismatch and there's only a cost at this interface of one unit cell? And through more electron microscopy, what was found was actually that this is the case. So you can really see here, this is basically electron loss microscopy. I shouldn't explain what these different points are, but the basic point is that this material, this is where the material is metallic and insulating at room temperature, so it's in that range. And you can see that the materials are not bulk-like only for like 1 or 2 unit cells. Okay, but one of the interesting things is this isn't the only thing that can happen. So in this experimental work from Professor what they found is you can take, rather than 2 different nickelates, you take vanadium dioxide and you also have vanadium dioxide with some oxygen vacancy. So take some oxygen out. So this will lead to some interesting physics because you might have say a single MIT and 2 structural transitions, for example. So the point then is that you can have the MIT separated from the structural transition. And this is what I was mentioning. This means that you can have these metastable states. So you might be able to have the switching of the MIT separate from the transition. This might actually be in reverse. There might be 2 MITs in one structural transition, but that's a separate story. The main point is that you can have these metastable states as well as electronic switching, right? So keep the same atomic structure, change metal to insulator. Okay. And here, one of the plans is just to combine these types of theory into a theory of phase transitions. right, and optimize real devices. As well as, apply the theory you have to things like VO2. Okay, so the final part is materials discovery. So how do we discover new materials? And there's a reason for it, is that, I've been showing you, for example, neodymium nickel, a bit of vanadium oxide, but the basic point is that what we really want our materials, as I was showing, TMIT above 300 Kelvin, so above here, sharp transition. Only one that we can really reliably use is VO2. Samarium nickelate is also here, but as you can see, and as you saw in the previous plots, not a very sharp transition, right? So again, we need high resistivity switching, transition temperatures, less material fatigue from electronic driven transitions. But and the other thing to mention is when we're searching for MITs, there's always a nice possible benefit of finding a superconductor, right? So neodymium nickel oxygen 2 I showed you at the beginning is what you get when you take the metal insulator transition compound, neodymium nickel oxygen 3, and take out an oxygen. So these kind of charge fluctuations mechanisms may be related. Okay, so the challenge is that, there are many materials, many things one can calculate, right? There are complex electronic and electron lattice interactions like I was showing you. You can't really do high throughput simulations for this type of materials and then expect to get anything reliable is my impression. Maybe you can get where the atoms are, but not much else. And the tools we use generally are kind of like a 0 Kelvin theory. So it's except for the dynamical mean field theory I was showing you, which is absurdly expensive to try and simulate multiple materials that you don't even know can be synthesized. So then how do we do this? So this is all described in this paper. And, this is a collaboration between, Northwestern University and MIT. And importantly, we collaborated with groups to develop machine learning tools, right? So I use machine learning, I can build tools, but I don't think a lot about, the statistics that go into building new tools like, gradient boosted trees and so on. And the idea is to kind of have a different framework for materials discovery and understanding. So, take published work, you do human and AI searches, and of course, when you use Google Scholar, it's an AI search as well. But the reason why I kind of see that also as kind of a human search is that Google Scholar won't necessarily tell you like about some MIT material that you don't know about. It'll generally recommend papers to you, probably that you're likely to click on, right? So they're going to be stuff that you've maybe read about. They're going to be the papers that are in Nature. They're going to be papers maybe from the past 10 years. And people always make discoveries from just reading a paper from the 70s that solves one of their problems. I think this was part of the story actually of the Nobel Prize in chemistry this year, was like one of the grad students solved a problem by reading a paper from a few decades ago. So, and a lot of times this is actually how new materials are discovered, like their functionality is discovered. Someone synthesized them, didn't look for X material someone is really an expert in, and then someone discovers, well, this does have this property I care about now that I tried it. So this is kind of why we need AI searches to help kind of reduce the bias of what we normally find. Okay. And then you build a database, and then we can do some experiment, we can do some theory. Well, I can't do the experiment, but we can do machine learning. Machine learning can maybe also help us separate materials that have properties from others. Maybe machine learning can recommend new properties or new materials. And we have some new predictions, we have some new validation, we have new published work, and this can keep growing. And the point is to integrate machine learning in all these different steps. And I should also probably integrate machine learning into the synthesis process. So the usual approach I've been showing you is to have many, many detailed studies on one material, like rare earth nickelate compounds, which I'm guilty of. So these are and actually a slightly outdated list of the papers I have on rare earth nickelates. I should add a few more. And the issue with that is, right, you can build really nice models, but you tend to overestimate the importance of what you can calculate, right? So you can calculate neodymium nickelate super well. That might not apply to another MIT material. Scuteridites, for example, that we found out about are actually very different in terms of how you think about their electronic structure. And the basic point is, if everything you have is a hammer, everything looks like a nail, right? So you want to just keep finding things related to what you know. Machine learning, in some sense, is the opposite approach from the usual. Compare all known compounds, identify new features, and hopefully go a little bit outside of domain knowledge by having this kind of wider perspective. Of course, machine learning is best at what it has already looked at. So you have to be careful when you go outside of this domain knowledge. But the idea is to have kind of a big picture view. So the first thing we have to do is build a library of all the metal-insulator transition compounds we know. And the challenge is that there are very, very few compounds that actually have this property as a function of temperature, and they have a very diverse set of mechanisms here. All right, so this makes things hard. But what we've done is, working with Aubrey and Elsa, we gave them some keywords, which they then used to search through many, many papers they had, down selected like 70,000 papers. And then we kept going. And this allowed them, for example, to suggest a particular material. And, we'd put this material type in one of the keywords, and they could find some more. We could search for that material type on Google Scholar. And we can just keep going until we built this database. So, the difference was going from probably like 40 to 60 compounds, which is quite a lot if you think about it. And we have this resulting database, which has like 360 compounds. So the other compounds are not MIT materials. They're similar in atomic structure and the types of atoms they're made of, but they're not actually MIT materials. And that's because if you want to train a machine learning model, you also want to tell it what isn't an MIT so that then it can classify yes or no, right? And the classification here is done using experimental structures. So we only put things that have been confirmed experimentally to be MITs, and we put in the experimental lattice structures. So yeah, so this is actually like 360 now. 68 total MIT compounds. So this database is constantly, we're happy to update it. We're happy to update the classifiers. We get more compounds. And basically, we have this very easily accessible database. If you just click on this link, it's very simple to use. So, this is the Rondinelli Group website. You go here, you can hover, you can see different features for different compounds and so on. I should mention the Hubbard U's are quite large for materials that are actually more covalent than ionic, because then the charge calculation isn't particularly accurate. But that's only really the case for scuteridites. All right. So the other thing is this: we built this machine learning model to separate MIT from non-MIT compounds. And one of the very cool things is you can then look at features, and you can look at the materials, and you can see how we put in the classification. And then you can also see, and again, these do not have a Hubbard U of 60. This is an issue with charge counting. You can have the scatter plot of the different compounds. And then you can bunch them, by eye and say, well, there should be more MITs here. But then the interesting thing is that the MIT classifier actually makes a heat map And for example, yes, here where most of the MITs are, you can probably keep searching for new ones. This is where the red says this should probably be an MIT based on these two features. But then if you're here, this doesn't contribute anymore. So this tells you there must be other two features that lead to a positive classification here that are not these two. So it can kind of tell you where is the role of these two features important and where it isn't, right? It's a little bit different than just like drawing a circle around every group. And this pipeline, I should mention, is built by an undergraduate student who is in our group, Peiwen, who actually won the highest award from the department for this work. And it's actually, it's in this link, which will take you to the binder, and it will run in your browser. It takes a few minutes to install the first time, but then you can just run it, and then you can upload crystal structures from materials project and see what classification do you get. So, right, you can see here, you go through this. I know generally tools in Python, if you build one, it's great to have them available in this way. Okay, and you can then see the classification here and what led to that classification using various shock values and so on. Okay, so you have this pipeline, you upload the structure, you get some probabilities. Take it with a grain of salt. Again, anything that's not already like in what's known, I see it a little bit more as a filtering tool, right? So you can have this filtering tool. You take compounds from a library, you put them in this classifier, you do some density functional theory calculations, hopefully paying attention to each calculation, and then propose them for experimental validation. So, experimentalists who are interested in synthesizing, these are some interesting compounds. This one in particular has a very interesting semi-2D lattice structure, which should have some interesting spins. Okay, so we have these compounds, we have this paper, we have these databases, and hopefully this should help accelerate the discovery of new materials with people using these tools, including myself. Okay, so I've talked a bit about local theory and control, like how do we build these theories for these materials, heterogeneity, and how to study it using material sandwiches and materials discovery. So thank you.
Was vaguely familiar with the superconductors, but this detail of like how we could start to try and understand them better is just really fascinating.
Thank
So
you.
I will go ahead and jump straight into the questions, and for everybody in chat, certainly feel free to ask more questions as well as we go. We'll just keep going until we're out. So let's see. It seems like a number of these superconductors have more exotic atomic components. Does that limit the uptake, or I guess the utility of these?
Yeah, so yes, you generally, and this is generally where I think the field is trying to go, which is we're really trying to move away from things like neodymium, right? Where they're not a key part, right? The superconductivity there is from the nickel, right?
Mm-hmm.
Superconductivity is often from iron. So you find they're not all transition metals are particularly easy to find. Copper is a problem, right?
Mm-hmm.
But generally, I think we're kind of trying to figure out how do we start moving away from rare earths in particular. Mining, they're in a few places, and then when they're extracted, the result for the environment there is usually not great,
Sure.
right? So
Yeah.
neodymium I think neodymium is used maybe in some of the magnets in electric vehicles, like laminated magnets, I think. So a really key part of what I'm kind of doing, moving forward, and this materials discovery part is trying to figure out new materials that have these cool properties, maybe have them at higher temperatures,
Yeah.
but you know, we don't need to mine neodymium underwater, something like this. It's not good, and it's not sustainable. Right now, the other issue is with these materials is that the cuprates can maybe be used, but they're often kind of frail ceramics. They're oxides. That also makes it a little bit harder to use a lot of compounds. And that's, for example, say graphene, and bilayer graphene. Well, it is superconducting. It's super low temperature, but it's all carbon. It's great.
Yeah.
So I think that's also why there's been interest in these types of things. The 2D chalcogenides, and they don't really have this issue.
Okay, no, that's a good point. Let's see. How do defects like missing oxygen atoms affect the breathing mode of, for example, the nickelate you described?
So that's actually, I don't remember what oxygen atoms in particular do. I think they often suppress the transition. And there's and that's something people find with like epitaxial strain, is if you strain them too much in one direction, they start having oxygens missing, and you kind of kill off the transition. And then there's other things you can do instead, like add hydrogen, which actually go the other way and make the transition maybe stronger. I think it was hydrogen or helium. Sorry, I don't remember this particular word.
That's
but,
okay.
But yeah, defect tuning is interesting. The oxygen vacancies usually tend to suppress the transition, but they can also be very useful, right? So like the neodymium nickel oxygen too, where you deliberately cut off a layer of oxygen and make it superconducting. This leads to kind of some questions like, could we have other forms of oxygen vacancies in an ordered way rather than but yeah, I think generally this is a bit understudied overall.
Okay. Maybe somebody will take a look at it. That'd be great. Let's see. Are there any benefits to having a higher transition temperature, metal insulator transition?
It depends, right? So you want it to be above room temperature, because you want to have it insulating, and then you want to switch it, right? If it's a metal already, then it's disordered, and you can't, because most of the things we add to cause a transition are kind of messy. Like you shoot it with a laser, or that's maybe the least disordered thing you can do. You add an electric field, you heat it up. All these things kind of push it towards a disordered state. So that's why you want to have a TMIT above 300. Now, the question is, how far do you want to go? And at some point, if you go very high up, so showing these memristors using, I think, niobium oxide, and that has a very high MIT. So that ends up meaning, but it's also very easy to grow. Well, easy. I can't grow thin films, right? But it's an easy to grow thin film compared to others. It won't have as many defects and so on. So it's more controllable. The downside to using that is that it has a high transition temperature, many hundreds of Kelvin above room temperature. And what that means is that you need high electric fields to make it switch with an electric field. Now, how the two correlate is a bit trickier, but the result is that it wouldn't exactly be fast or energy efficient to use it. You probably want, maybe something more like VO2. I'm sure there's some similar devices with VO2.
Yeah. Okay.
The VO2 you saw breaks, so then there's other
Right.
issues.
Yeah. Let's say that was an interesting point that you brought up that I had never heard about before with VO2, because I've seen some work with VO2, but nobody's ever mentioned that that it's not just a perfect material. So that is interesting as well. But you did mention, and it may not have been VO2, but you had that the smart window that you talked about with
Yeah.
you have a layer of your the material that's transitioning, but you talked about how you could pull electricity from it. Could you talk a little bit more about that?
Oh, I haven't thought too much about that. Huh. No, I mean, I was just thinking there, I was just showing how it would turn into a metal. But yes, I mean, I didn't think about how you'd build it into a device, but that's a very good idea. I should write down,
Okay.
because I didn't think about that.
Okay. Yeah.
Um, yeah. Um, yeah, I haven't. But in general, correlated compounds have a band gap, charge transfer energy.
Sure. Okay. That makes sense.
Yeah.
Okay. So how large are the perturbations that lead to Yon-Teller distortions? I think this is where you were talking about how you started to figure out the better way to simulate them.
So that's, I guess it depends. So for example, for the nickelates I was showing and all these things, I guess the breathing distortion, you can also kind of think about it as like a multi-center Yon-Teller of some sort. But it's really fine. So it's like 0.08 angstroms or so.
Wow.
Yeah, so it's tricky to work with these things, right? That's why, I keep mentioning how awesome our experimentalist collaborators are.
Yeah.
Huge effort is measuring things, like measuring like a little bit of oxygens. Which way did they? Because I'm showing these things that just move, like you have this breathing
Yeah.
distortion, but in reality, like there's some rotations. The rotations might also have like the rare earth moving up and down, and the question is which way is it moving?
Yeah.
And it's really very, very fine procedure to like grow the thin film atomic layer at a time, slice it, and then look at it one atomic layer at a time. And not just one atomic layer, it's an atomic row basically, right? Because they shoot through the sample and it just goes, say, through the X direction. So the experiment is very tricky. For theory, it's a number. We can rescale it, but the DFT calculations they're pretty interesting. Particularly, the more fun thing was, we had some experimental structures for the bulk materials, and then there was this question of how do we simulate a heterostructure where we can't really get the breathing distortion amplitude and the structure, because it just can't be measured, right? If you have a bulk material, you can really resolve that. If you have a heterostructure and each layer is different, it's a little bit harder.
Oh yeah, absolutely. Well, especially if you're
So
talking about, like you said, growing like an atomic layer by layer structure. I mean, that's just
yeah.
I don't know how you would do that.
So then the question was, how do we simulate things? And basically, my approach is usually simulate the bulk and then repeat the procedure in the heterostructure. And one of the tricky things, well, this is actually published already. I don't know why I said in press, but anyway, but the thing there was also, how do we change this breathing distortion in a way that's realistic?
Yeah.
because now we don't have this uniform bulk material. We have a heterostructure.
Mm-hmm.
And there, what I did was this breathing distortion is correlated to the electronic part, and the electronic part is driven by electron interactions, or basically you can think of this Hubbard U term, but this Hubbard U term is more or less the if you think of like electrostatic interaction between the electrons on the orbitals, that's more or less what it is, right?
Okay.
So you can change that, and as you change that, you will get a breathing distortion that's bigger or smaller. And this way, if that works for the bulk, then I can do that for the heterostructure. And there's this in this paper, in the PNAS paper I was showing, those, which, I mean, I guess I didn't put them here. They're easy to find in my Google Scholar. That gives you a very good estimate, I think, of what's actually happening in the material, and how basically if you grow one material on the other,
Yeah.
you'd basically say this material wants to have a breathing distortion, this one doesn't.
Okay.
So then this bond here, this nickel oxygen bond that goes towards this other material, is basically stiffer. That's the equivalent, because this other material doesn't want to do the same thing.
Yeah.
So it's kind of this interesting thing to simulate and then actually try and understand.
Yeah, I can see where that would get very, very complicated. I guess if I'll piggyback off of that, just to this is my ignorance of the theoretical side of things. How do you, in a situation like that, where like let's say the layer by layer heterostructure, how do you have a sense of whether or not the results that you see are not necessarily correct but reasonable? I mean, I'm sure there are extreme cases where you go, okay, that makes absolutely no sense at all. There's no way that's right. But if you're sort of in the like, the theory gives you an answer and it's not just absolutely ridiculous, how do you start to go, okay, this is a reasonable answer? We can probe more deeply into that.
It's hard to know, basically. The thing I will say, so some things that give you a good hint you're looking at the right direction is some atomic structure distortions that can be pictured. You're maybe not just fitting them, you're predicting them. So I have this paper, we're trying to build a cobaltate superconductor, and it didn't happen. Ended up an insulator, obviously, otherwise people would have known about it.
Okay.
There's a heterostructure of a cobaltate and a titanate, and there was an electron transfer from the titanium to the cobalt. So that was kind of how you engineer these perovskites, and the point then was to have something like in the nickelates. We had been doing this with nickelates before. And then the thing I found was, well, this moving of an electron, the oxygen is negatively charged, and it actually moves. So it really moves towards the titanium, which is now very positive. And it got like 0.4 angstrom predicted. And we're like, well, this is a lot. Can you look at this with some microscopy? And and they found it. They found 0.4. And that kind of starts telling you this is the right picture.
Yeah.
The tricky thing was like the material was insulating. Why is it insulating? And that's a little bit harder, especially because we had this very nice like dimer picture. It's like in VO2 basically. But in practice, these are 2 unit cells of material. It can, if between other insulators, it can be insulating for so many reasons. Like, it can just have defects. It can just not be cobalt. It can just have migrated and be partially titanium. You just don't know. So that's it's a little bit harder when you start going towards like the electronic picture. It's just like, the way I think of it is, am I sometimes like predicting things rather than explaining them after? And often it's also like, is like a minimal model predictive? right? So for
Yeah.
the heterogeneity part I was showing in this paper, for that phase diagram with like 1 or 2 transitions, there was like, okay, I have something with 3 parameters getting this super nonlinear curve.
Yeah.
Well, probably right. But
Okay.
and I mean, I have 2 more papers I think coming out in that direction, and they've
Okay.
just kind of kept showing like this really works,
Okay.
and it's great. But yeah, it's often very, you never fully know. And the other thing I should mention is the following. You saw, what I don't show is a lot of times there's some tunable parameters in the models, right? There's like
Sure.
some U and some J, and people might not like that. They might say, well, this is fine tuning. That's true. You can fine tune things to get an experimental result. But what I find, and if you get most of the experiment right, it tells you maybe you did fine tune, and that's fine, but that's maybe the right picture.
Yeah.
But the other interesting thing to me is, what do you do if you change those parameters?
Yeah.
We're not trying to confirm experiment anymore. We're trying to figure out what leads to the experimental results. So if you change things like, the Hund's interaction, which is, what aligns spins like we've learned in chemistry, what is the role of that, right? So it can be actually pretty interesting to also make theory go wrong on purpose, to see what actually pushes you the right way.
Yeah, no, that makes a lot of sense. I think this is our last question, but it's a good one to end on. I think it's a little bit open-ended, so I'll be curious to hear your answer. How can you continue to improve the machine learning filtering and prediction tools that you described?
Well, it's difficult.
Sure.
The difficult thing with this is, we have like 60 something compounds.
Yeah.
We couldn't train a neural net on, that needs thousands. So okay, we could use trees, and try really hard not to overfit. This includes, say, not having too many features, right? If you have 60 materials and you have 200 features, you're probably not doing well. So we reduce things to 10. That was important. But ultimately, the most important thing is, people, including me, say, use this tool, discover new materials, discover maybe some materials that are not MITs for sure, because we look at the literature and a lot of times someone says something is insulating and you read it and it's like, but are you sure? You measure to room temperature. That's not enough.
Yeah.
Right. So, and it looks like things are changing at some point. So maybe you should have went up 100 Kelvin more and seen what happens. So we don't, the limiting factor with this is the scarcity of materials, and that's the limiting factor for these correlated electron materials in general. And the real only way to make this machine learning process really work significantly better is to have new materials. Because 60 with them all very, very different, most of them oxides.
Yeah.
There's a few sulfides in there. There's these scutaridites, but it's tricky without just having more.
Yeah, that makes a lot of sense. But I guess it's good to know too that it should get better as this, as the feedback loop continues. You'll get more compounds. The machine learning method gets better, and that might give you even more insight into potential other materials as well.
Yeah, and the other question is also the models we're building, right? So we right now, like, there's a particular set of features. So the features we use, some of them are things like the Hubbard U I was mentioning, charge transfer, so things you kind of expect. There are certain things I didn't go into a lot of detail, but it seems to find certain structural properties to be interesting, like how different the atoms are in size.
Hmm.
So we kind of know of this in oxides and perovskites as a tolerance factor, but it seems to find this thing called average deviation of the covalent radius, which is
Hmm.
very similar. And it's actually in oxides, it's like linearly proportional to it, but it's more
Okay.
general. And
Yeah.
then the question is, can we maybe have features that are more predictive? Can we maybe build more? Can this inform, say, new models? So
Yeah.
then if you have some new models, just like we thought some nickel that can be superconducting if you make it orbital ordered enough and make it kind of D9.
Yeah.
Maybe we can make something similar with other materials and
Yeah.
maybe make them more
Okay.
useful and not have errors.
Okay. No, that makes a lot of sense. That's really cool.
Thank
Um,
you.
I think that's all the questions we have. So I will say thank you again to you, Alex. Like I said, this was very interesting. It's always I always really appreciate seeing theory that is validated with the experimental work as well, and then feeds back into more experimental work, and you show that it's not just a fitting of previous experimental data, but you can actually use it and turn it and say, okay, here's where we can go from here with it.
Yeah,
That's
so
just super cool.
maybe I should go back to the slide that
Sure.
actually had the actual yeah. So so the thing I'm not actually mentioning is that, right, so this is the paper with the electronic and lattice part.
Hmm.
This was actually, we didn't start by trying to do this. We started because we had this method developed here,
Hmm.
and it wasn't really giving us it wasn't giving us energetics we wanted. So
Okay.
it wasn't giving us energetics, period. That was kind of the problem. We had some intersection
Okay.
of plots. Which one is the minimum? We don't know. But so here we were like, we really need to find a way to figure out which one is the ground state and how does it change,
Hmm.
because we were trying to help out some experimental colleagues, and other methods, DFT, were like really overestimating some numbers.
Yeah.
So really, like, let's look at this model we really like and see what's happening. So there will be, that experimental paper should hopefully come out soon as well, or
Okay.
experimentally driven paper.
Yeah.
But that's how this started.
Okay.
That's how most interesting theory questions start. Is there a real question that someone wants answered?
Yeah. Absolutely. No, like I said, it's just really it's super cool to see how it was developed and refined and just like I said, the fact that you can take your theory work and confirm it experimentally just shows that you did a really great job
Thank
understanding
you.
what you were looking at and developing that model. I've seen some theory that was that did not follow experimentally very well. So like I said, it's just really neat to see how you did this, and I appreciate
Yeah,
you sharing it
and
with us.
the thing to mention is also when very often experiment won't match, right? So in the
Hmm.
heterogeneous part, you just don't have like temperature dependence in the theory. This type of
Yeah.
calculation that's very complicated, I was showing, that corresponds to like first order transitions. You
Yeah.
can't really do it
Oh
for
yeah.
those heterostructures. Um, right. The DFT method that you can do, that's a second order theory. So then it wouldn't have this like phase boundary that's really needed for like nucleation type models.
Yeah.
So then we build a lambda model. Like, we can just write something pen and paper, and um, that's great. Theory was used to exclude what isn't the cause there,
Yeah.
actually, I should.
Oh, then that's fantastic. Like that's another great use for theory as well, is to narrow down what you actually need to look at as well. That's
Yeah.
that's an excellent use for it. So thank you again. Like I said, that just really well done. You did a great job explaining this. I am not in this field at all, and I was able to follow the work that you were doing, and that speaks
Oh, awesome.
to how well you presented everything. So thank you again. Thank you to everybody for coming out. Really appreciate you asking the questions, listening to the talk. And I hope you will all come back out next week. We'll be here next Friday at the same time. And let's thank our speaker one more time. Really
And
appreciate it.
one thing I should mention, maybe again, is why is this doing this again? I do have like some very pedagogical talks here, so different, kind of slightly different topics, chemistry view of physics, stuff like this. So similar style.
Very good. Yeah, I'll make sure we put that in the description of your talk.
Awesome.
So that people can find that, and I'll get you to send me your link to your Google Scholar page as well. That will make sure people can dig more deeply into the papers that you referenced, so they can learn more about the great work you've done.
Yeah, thank you so much.
Awesome. All right, let me get you to hang around for just 1 second. We'll talk very briefly, and again, thank you everybody else for coming out. I really appreciate it, and we'll see you next week.